Today, we're diving into one of the biggest mysteries in the universe. Think of it like a cosmic detective story. The crime scene? The entire universe. Our witnesses? Well, they're ancient light and exploding stars. And the problem is, their stories don't match up. Okay, so we've known for almost 100 years that the universe is expanding. That's settled science. But how fast is it expanding? You'd think we would have a solid answer to that by now, right? Well, here's the thing. Our two best ways of measuring it are giving us two completely different numbers. And I'm not talking about a tiny little difference. It's a huge, glaring conflict. And just so we're all on the same page, this is not a simple rounding error. I mean, these are our most trusted, most precise methods for measuring the universe, and they are fundamentally at odds. For a while, scientists called it the Hubble Tension. Sounded kind of polite. But now it's escalated to what everyone is calling the Hubble Crisis.
All right, so to really get what's going on, we've got to go back to the beginning of this whole thing. And for that, we need to travel back to the 1920s, to the man who started it all, the legendary astronomer Edwin Hubble. He's the one who first discovered our expanding universe.
So back in 1929, Hubble figured out that all the other galaxies were moving away from us. This was the first real proof that the universe was getting bigger. For years after that, scientists worked on refining his measurement. But then, pretty recently, things got complicated. See, when we look at the early universe, like its baby pictures, we get one speed. But when we measure the universe as it is today, we get a different, faster speed. And that right there is the heart of the crisis. So this is the conflict, boiled down. It's kind of like a cosmic tale of the tortoise and the hare. Our models based on the early universe predict a slower expansion, the tortoise. But what we actually observe in the universe today is a faster expansion, the hare. So which is it? Is one of our measurements wrong? Or could they somehow both be right?
Okay, so let's dig into the evidence. To solve this mystery, we have to look at our two key pieces of data, our two witnesses, if you will. The problem is, their testimonies just don't match up.
First up, we have the early universe. Our clue here is something called the cosmic microwave background, or the CMB for short. Think of it as the oldest light in the entire universe. It's literally the afterglow of the Big Bang. It's like a fossil. A snapshot of what things looked like when the universe was just a baby, only about 380,000 years old.
So scientists used the Planck satellite to study this ancient light really closely. And from that, they calculated the expansion rate of the early universe. The number they came up with was 68 kilometers per second per megaparsec. And a megaparsec is just a ridiculously big unit of distance, about 3.26 million light years. But the important thing is the number. Remember it, 68.
Okay, on to our second clue. This one comes from the later or modern universe, and we're not looking at ancient light anymore. Instead, we're looking at these incredible exploding stars called Type 1a supernovae. The reason they're so special is that they're what astronomers call standard candles. Basically, they are like perfect 100-watt light bulbs. They always explode with the exact same brightness. So if you see how dim one looks, you can figure out exactly how far away it is. It's a brilliant cosmic measuring stick.
Right, but this is where it all goes wrong. When scientists use these supernovae to measure the expansion rate today, they get a totally different number. The measurements point to a speed of around 74 kilometers per second per megaparsec. And there you have it. That's the crisis. The early universe gives us a speed of 68. The modern universe gives us a speed of 74. They can't both be right, or can they? And again, this is not just a rounding error. It's not a fluke. This gap is real, it's persistent, and it has been confirmed over and over by different teams using different instruments. It really seems like the ancient universe and the modern universe are telling us two different stories. So, what in the cosmos is actually going on? Okay, so when you have two conflicting eyewitness accounts in a detective case, what do? You start looking for suspects. And that's exactly what cosmologists are doing. They've basically got a lineup of 3 prime suspects that could explain this whole mess.
So, who's in the lineup? Suspect number 1, simple mistake. Maybe we just messed up the measurements somehow. Suspect number 2, unknown physics. Maybe our understanding of the universe is fundamentally missing something. And suspect number 3, a flawed crime scene. What if it's all about where we are in the universe? Maybe our location is throwing off the results.
All right, let's take a look at suspect number 1, a simple mistake. Could all of these incredibly smart people just be wrong? Well, this is probably the least likely culprit. These results have been checked and rechecked and triple-checked by so many different groups. The chances of an error are now less than 1%. So we can probably rule this one out. The numbers seem to be solid.
So that brings us to suspect number 2, and this one is way more interesting. Unknown physics. You have to remember, 95% of our universe is made of stuff we call dark matter and dark energy. We know it's there, but we have no idea what it is. So what if those mysterious forces are doing something weird, something we haven't accounted for? If this is the answer, it means our entire standard model of the universe is incomplete. It would literally be a revolution in physics. But hold on. Before we go and rewrite all the physics textbooks, there's a third suspect that's been gaining a lot of ground lately. And what's really cool about this one is that it doesn't require any brand new physics. It just requires us to think a little differently about our own address in the universe. This theory basically asks a simple question. What if we just happen to live in a kind of strange part of the universe? Specifically, what if our galaxy, the Milky Way, is sitting inside a giant cosmic bubble? Or, to be a little more accurate, what if we're in a huge, relatively empty patch of space called a void? Now, when I say void, don't picture completely empty space. It's not like that. A better way to think about it is like a cosmic suburb instead of a bustling downtown city. There's still stuff here, but it's more spread out. This particular void is enormous, about 1 billion light years across, and it just has about 20% less stuff, galaxies, stars, matter, than the universal average.
So how does this solve our mystery? Well, this is the really clever part. If we're inside this less dense bubble, that means there's less matter all around us. Less matter means less gravity pulling everything together. So with less gravitational pull holding things back, the stuff inside the bubble, well, it would naturally expand away from each other faster than the average for the whole universe.
And just like that, the whole conflict could be resolved. That number, 68, that we get from the ancient light, that's the true average speed for the entire universe. But the number 74, the one we get from nearby supernova, that's just our faster local speed because we're inside this bubble. All of a sudden, our two witnesses aren't contradicting each other anymore. They were just describing different things, the local speed versus the global speed.
Now, as neat as the cosmic bubble theory is, it's still just that, a theory. It's a leading suspect for sure, but the case is still wide open. So the big question remains, is this whole crisis just a cosmic illusion, something that boils down to our unusual address in the universe? Or is this tension a real clue, a crack in our understanding that's pointing us towards some revolutionary new physics? Whatever the answer turns out to be, you can bet the final verdict is going to change how we see our place in the